Hi, in this example, we want to look at using marginal model plots to tell us how to transform our target variable. Okay, so this is an example from the textbook, and here is the website. So remember, the textbook is a modern approach to regression with R, and the textbook is free for UCF students to download through the library. All right, so let's go ahead and let's load the data and start working through. So just like always, load the data, get in there. Then one thing I like to do, because of some of the plots that are produced for regression models, I like to have my data ordered by an important variable. And so I usually order it by the target variable. So I go ahead and sort it. And when I do this, I change the row names so that the row names are going to be numbered 1 to n, and they're going to be correlated with the Spearman correlated perfectly with the target variable. That way it's a little bit easier to detect things. When I see things printed on the plots, the diagnostic plots for the linear model, it kind of, if I see a small or a large number or something in the middle, that can help me spot what's going on easier. All right, and something I always do, I always color my points by a variable. So I'm going to color them by my target variable, and I'm using the Viridis color palette because that is a good color palette for those who are colorblind. It's not perfect, but for that purpose, there is no perfect palette. All right, so right off the bat, right out of the gate, now let's actually start doing some statistics. So what we're going to do, we're going to go ahead and we're going to do a scatter plot matrix. We're going to use the pairs command, and we're going to just plot the 3 predictor variables and the target variable. All right, so here I can see that we've got defective and temperature, and there looks like there's a relationship. Defective and density looks like there's a relationship, and defective and rate looks like there's a relationship. Now, I want you to notice that, hey, that to my eyes, that looks a little bit curved, just maybe. That looks a little bit curved, maybe more so, and that looks like it has a little bit of a curve, maybe, maybe not. I'm not really convinced yet, but it's something that's in the back of my mind. I notice it. Now, there's something else I notice when I look at this. That looks like a straight line to me. That looks like a straight line to me. And that looks like a straight line to me. All right, so what that tells me is that potentially at this point, temperature and density, or temperature and rate, or density and rate could be telling me really the same information. It could be that there is some, like maybe there's a 4th variable floating around that's a driving temperature, density, and rate, and really that's the variable I truly want. But so from my point of view, 1 or 2 of these predictor variables are redundant, possibly. Now, when I see this type of situation, I always want to be worried about overfitting, because what will happen, let's say in reality, I only want temperature. If in reality, all I want is temperature, but I go ahead and include density, it might be that temperature's coefficient gets really big, but then density's coefficient goes negative and big also. They cancel out so that together it ends up giving me a good fit, at least on the observed values. All right, so what this would do is that the slopes can counteract each other for temperature and density. Now, in a higher dimensional sense, it can get a lot more complicated when we have collinearity. It could be that density and rate account for all the information in temperature when they're together, but not when they're present individually. So that's something to watch out for. So this is why we need to always do variable selection. Now, these issues with collinearity and overfitting on a model, the more data I have, the less I have to worry about. But remember, the more predictors I have, the more prone to overfitting I am. That will always be true whenever you're doing a regression or classification model, anytime you're doing supervised learning. Okay, so keep on going. So first and foremost, let's go ahead and build that vanilla regression model. All right, what I'm going to do, I'm going to take defective, and I'm going to say that it depends on temperature, density, and rate. Okay, so now, after I build the model, I'm going to run summary just to see, hey, what did I get? What does it look like? Well, something that jumps out at me right off the bat is I see that temperature, it's statistically significant, but not by much. It depends on your criteria. If you say 0.1, that's statistically significant. If you say 0.05 is your cutoff, then that's not statistically significant. None of them are. All right, well, that's kind of unsettling, and density and rate are not statistically significant. That means that it's possible that the correct coefficient is 0, 0, and 0. In other words, we don't want to keep these in the model. All right, well, that's kind of unsettling. Even though when I looked, I saw a relationship on the scatter plot, right? Now, something about this is I've got 0.87, 0.88 r squared. But when I look, I mean, I can see trends here. So I'm feeling like there's something going on. So, I mean, this is like a stronger result than I would expect when I've got all statistically non-significant predictor variables. All right, let's go ahead and do the ANOVA test. And so here, now this says that adding temperature is a statistically significant improvement over the mean model. Adding density to the temperature model really is not statistically significant at the 0.05 level. And then adding rate to the temperature and density model is not statistically significant by a substantial margin. Okay. Okay, so now let's go ahead and let's do a lowest model. All right, so notice on this plot, I've got my scatter points and I've got this curve going along here. All right, so what did I do? I did a lowest model. So what I'm going to do, so what is lowest? So what this is actually doing, this is a polynomial regression, but it's a local polynomial regression. So what it does, it takes only a few, so at each individual point along the predictor variable, it just takes observed data points that are close. In regular regression, regular regression takes the entire data set to build the model. Here, if I want to know about, let's say when x is equal to 2, what it does, it'll take like, 1, 1.5, 1.75, 2.1, 2.3, 2.5, stuff like points like that, points that are close to the predictor value that is of interest. So it does a local polynomial regression. And so this has a lot of flexibility in it. Now, something to worry about is that this will overfit. And frequently this will overfit on the far left and the far right, on the extreme values of your predictor. But in the middle, my impression is that this is pretty good. And you can usually tinker with the settings of it inside the function to get it to be even better. So when I take a look, when I plot the lowest model, it looks pretty good. Now, what kind of shape from college algebra would that look like? Maybe like a quadratic, maybe, possibly. I don't know, maybe. So this is what's nice about this is that this kind of gives me an idea of what I should try if I'm going to try a transformation. All right, and we go ahead and get the FID values, and we get the so here we got the FID values from the linear model, and here we get the FID values from the lowest model. Now let's go ahead and plot. Let's plot our FID values versus temperature. And you notice that things are, that's pretty tight. All right, so if I plot my observed values, and I plot my predict values, and it looks like a straight line, I probably have a pretty good model. All right, so in marginal model plots, what we're going to plot our scatter points. We're going to lay down our model. Our model is going to be projected onto the plot, and if a smooth a smooth fitted curve, such as the lowest model, is close to the model that we have printed, if they're close to each other, then that reassures me that I have a good model. All right, so here I notice there is a deviation. So the straight line is my linear model, and then the curve is my local polynomial regression model. And we go, it's a little bit off from each other. Not like crazy off from each other, but that's a little bit off. So that makes me kind of concerned. All right, let's do it again. Let's do another marginal model plot. And here, along with temperature, I see that the local polynomial regression gives me a curve, and the model is a straight line. And it looks like there's a bit of a deviation between the two. All right, let's do this for density. And they're pretty tight here, pretty tight, then it deviates, and then it goes over here. So I'm looking at this, and yeah, I'm thinking things might be a little, my linear model may not be the best one to go with. And let's do it for rate. And once again, we get the same thing, really. So we can see that the data, if we're using local polynomial regression, the data says that there's more curvature than what a straight line can account for, which, so a straight line model is not sufficient. All right, well, I was looking at that, and it kind of looked like a quadratic to me. Well, as a first try, let's try to do a square root transform on our target variable. Because if I do that, then I'm automatically getting a quadratic generated. Let's go ahead and do that. So here I'm going to change the model. So I'm taking the square root of the target variable. Now this is a good way to get a quadratic going on these terms without having to induce a lot of complexity in the formula. Remember, in general, if I want temperature squared, I want temperature also. If I want density squared, I want density also. If I have rate squared, I want rate also. And I can do that. But if you think about that, there's going to be a lot of coefficients to be fitted off of that. If I have a smaller data size, then, I mean, that's a lot to be working on. Here, I'm keeping it down to three, well, honestly, 4 parameters. So 3 coefficients for temperature, density, rate, and then the intercept. And that's going to dictate everything about the model. Now, if I was to instead basically make a quadratic over here, I would have temperature, temperature squared, density, density squared, rate, rate squared, and then the intercept. I would have 7 parameters to fit. With the square root technique, I have 4 parameters to fit. I'm getting a simpler model. So if I can fit a pretty good model with just 4 instead of 7, I have a better model. Because it's simpler, it's going to be easier to work with, easier to interpret. Now when I do that, we see that all of a sudden temperature and density become statistically significant at the 0.05 level. Rate is not. And running the ANOVA test says that adding temperature to the constant model is an improvement. Density is also adding density to the temperature model when we have the square root of the target variable is a big improvement. But we can see over here that adding rate is not a statistically significant improvement. All right, so now let's go ahead and do marginal model plots off of this. Let's see what it looks like. All right, so my local polynomial regression model, the blue, is pretty close to the red. So that indicates that, or this plot indicates that this is a pretty good model. All right, now let's take a look with respect to temperature. Wow, the red and blue are right on top of each other. I'm feeling good about this. Let's look at density. All right, so here I've got a little bit of wiggling around. So remember, whenever we're doing local regression models, such as this one, such as the blue, it's going to wiggle around frequently at the far left and the far right for the extreme values of the predictors. That's just part of it. Here it doesn't wiggle around too much, so I'm okay with it. It could wiggle if it's only at the far left and not at the far right. I usually don't worry about it because though the local regression models are very sensitive to like the endpoints. If I have something a little bit off on my endpoints, and which happens a lot in real data because they're like the extreme ones, then I usually don't worry about it. I worry more about the center. Let's take a look at rate. And things are pretty much on top of each other. Now, something about this model, if I was using this for work, I would honestly take a look at removing rate from the model and keeping the square root transform. My feel is it's not adding anything. Mainly, I'm basing this mostly off of that initial scatter plot. I saw that rate had, it looked pretty well correlated with temperature and density, and then I see that's not really adding. So here, rate is making me vulnerable to overfitting on the model. So I would remove it, or I would consider removing it. Honestly, what I would do, I would take it out, build that model, compare the two, and decide on what to do after getting that information. All right, that's all I've got for you. Take care and goodbye.